Okay, so thank you all for tuning in to our mini CubeSat webinar series today. Thanks again to Bob for accepting our invitation to present in this series of webinars from the Taiwan Space Union. So our first speaker today is Professor Robert Marshall from the University of Colorado Boulder, SMED Aerospace Engineering Sciences. And the topic is CubeSats for space science. So Bob, whenever you're ready, please feel free to go ahead.
Okay, so again, thank you all for having me. Thank you all for joining and listening in here today. I'm going to talk about CubeSats for space science. And it's a very broad, vague topic, and I'll explain the title of the talk as I go forward. What I'm going to talk about, I'm going to do a very brief overview of CubeSats at CU Boulder. And these are missions that predate my time at CU Boulder. And into the present. Then I'm going to talk about 3 missions, which I've listed under this umbrella of CubeSats for space science. They're not all of the CubeSats for space science, but they're the ones that I am currently leading, called Apex, Canvas, and Cosmo. And so I'll spend a little bit of time describing each of these missions. Now, the reason I'm going to describe 3 rather than focusing on 1, for example, is to then sort of compare and contrast different approaches that we take in just these 3 missions, but also in other missions, to the CubeSat development. And there's a variety of things that we could compare, but I'll focus on just a few of them, and you'll see how I try to do that throughout the talk as well. So the first topic, just looking at a quick overview of past and present and future missions. CU Boulder has quite a list of CubeSats. Starting back in the mid-2000s with Dandy and CSSWE, shown here. These were launched in 2012 and 2013, as you can see. And CSSWE in particular was an extremely successful mission with quite a few science papers coming out of it, including papers in Nature. Following CSSWE was Minx, which you're going to hear a lot about in the next hour with Tom Woods, so I won't say too much about it, but also an extremely successful mission focused on solar physics, where CSSWE was more focused on radiation belts. QB50 was a mission that launched a few years after that, and this one was probably the first. Well, not the first, but it was one of the first developed entirely in the aerospace engineering department. A lot of these missions are developed at LASP, but they often involve the aerospace department and other departments, largely through collaboration and through student involvement. So these are past missions. Currently, there are, I made a mistake here, there are 3 missions on orbit that LASP and CU Boulder have developed and are operating. And those include Minx-2, CSIM, which is the Compact Spectral Irradiance Monitor, or Compact Solar Irradiance Monitor, excuse me, looking at the spectral irradiance from the sun. Polar Cube, which was actually developed through the Colorado Space Grant Consortium. Each state in the US has a space grant program. And InspireSat-1 I had listed here because I thought it had launched, but Lauren just corrected me and it has not launched yet, but coming up soon. So those are the closer to current missions, and then there's quite a few that are coming up very soon. CUTE is an astrophysics mission, and I believe it'll be the first mission that is designed to image exoplanets from a CubeSat. So stuffed into the 6U box is a telescope with a fairly large aperture that will measure exoplanets. CUE3 and Maxwell in the center are 2 upcoming missions that have been developed largely in the aerospace department through, with Scott Palo as the PI. And those are both also coming up for launch relatively soon. Now, the launch dates that I've put here, by the way, are the earliest launch dates. I think some of them are slipping back a little bit again. And then Serbi is another mission that's led by Shin-Lin Lee, who is in the aerospace engineering department and also at LASP. And Serbi is a new mission to measure the inner radiation belt electron population. That's another one coming up. And you'll see at the top there that I've said plus 9 more in development. These are just the next ones to go. And then there's quite a list of CubeSats under development. Another thing I want to quickly highlight in these 3 slides, if you look at the very top row, you see the sponsors for each of these missions. So many of them are sponsored by NASA. Many are sponsored by NSF, the National Science Foundation in the US. A few of them are sponsored by UNP, which is the University Nanosat Program through the Air Force Research Laboratory. And then within NASA, many of them are sponsored by different divisions, as shown here: heliophysics, earth science, astrophysics, and so on. So there's a variety of missions with a variety of sponsors. So now what I'll do is transition into talking about the specific missions that I'm leading. And I'm going to start with APEX. So APEX stands for the Atmospheric Effects of Precipitation through Energetic X-rays. And this is a mission focused on understanding the precipitation of high-energy electrons from the radiation belts. So in the picture on the right, I don't have a pointer that I can use, unfortunately. But in the picture on the right, just above the Earth, you see the word precipitation. And that is pointing to an arrow coming from, in this case, actually coming from the, well, it is from the radiation belts. And it's showing high-energy electrons coming along magnetic field lines from the radiation belts and colliding with Earth's atmosphere. And that is one of the main loss mechanisms for radiation belt electrons. And the mission goal is to understand this loss mechanism and quantify it to figure out how much is lost from the radiation belts and what is the effect of that population on the Earth's upper atmosphere. Now, in order to quantify that, we have to measure both the energies of the particles, the time resolution, of course, how quickly it's changing, the flux of particles, and the spatial scales. And a number of previous missions have made measurements like this, but they have made direct in situ measurements of the particles, and so they lack the spatial scales. So APEX is really bringing that as a new, unique measurement. So the slide here, I've kind of divided up into 4 quadrants, and I'm going to come back to slides like this for each of the missions. I've got the science goals there on the top left, which I just described. I'll talk a little bit about the management approach as we go forward, but for APEX, this is largely a collaboration between the Aerospace Department and LASP. So the Aerospace Department, which is where I am seated, we are developing the primary instrument for this mission. We have a secondary instrument being developed by the University of New Hampshire. And then LASP, the Laboratory for Atmospheric and Space Physics, I forgot to define that earlier. LASP is developing the spacecraft to house the instrument, and will also be conducting operations when the mission goes into space. So I say that it's split, but there's also overlap with students in our department helping with LASP and LASP helping with the instrument. It's very collaborative. We have a large number of students, and then we also have professional engineers that are working on that spacecraft development. What's new about this mission from a technological point of view, what I've listed as innovations, we're developing a novel X-ray imaging instrument that uses coated aperture imaging, and I'll talk about that shortly. This is something unique that you can't do with a big mission. You can really only do with CubeSats, is that this instrument was TRL-1 when we started. TRL is the NASA-defined technology readiness level. And so TRL-1 means it's a paper napkin idea, and TRL-9 is something that's been flight proven in a science mission. So we're increasing the technology readiness level as we develop it, where normally with a big mission, you need to start with something that's at a very high readiness. We're also developing some complicated solar panels that we have never built before ourselves. And we are in the chain of missions being developed at LASP that are implementing what they're calling the common bus. And I'll come back to that in a second. Like I said, this is a NASA, I didn't say this is a NASA-supported mission, so it's funded by NASA through heliophysics. Compared to the other missions I'll talk about, it's a good budget, compared to our NSF-funded missions, but we're still fairly tight compared to larger missions. This mission is focused on the science results. The education and training of students is valuable and important to us, but it's not the key focus from the perspective of NASA. And we're aiming for a launch date a little over a year from now. It'll probably end up being sometime early in 2023, just based on mission, launch availability. So a little bit more on the science overview. I mentioned this before. Previous missions, including Firebird, POSE, which are operational missions, they can measure the fluxes and energy spectra of electrons precipitating into the atmosphere. But they can't measure the pitch angle distribution, which is to say the angle with which these particles spiral down the Earth's magnetic field lines. And that determines where in altitude the energy will be deposited in the atmosphere. They also can't really measure the spatial extent. With Firebird in particular was a chain with two satellites with one following the other. And so if one saw a particular burst of precipitation and the second one saw the same burst at the right time delay, they could at least say that this is a spatial effect and not a temporal effect. But they really can't look at the full two-dimensional spatial scale of this event. So what APEX is doing is measuring particles, as you can see in the diagram, but also looking down at the atmosphere with this X-ray imager and measuring the X-rays that are backscattered by the atmosphere. So X-rays are only backscattered if electrons hit the atmosphere, so we know that these are particles that actually precipitated in the atmosphere. We can image them over a large region, and we can actually determine some details of the energy distribution as well by measuring the energy distribution of the X-ray photons themselves. Now I list here under complications that inversion from the X-ray spectrum to the electron spectrum is difficult. We'll talk about that a little bit on the next couple slides. And so to help with that, we added on the particle detector to provide a constraint on the energy spectrum. So I include this here. This is a little bit complicated, and so I'll just touch on it quickly to not confuse everybody too much. But what I'm showing here is a method that my postdoc and I derived a couple years ago, which takes the electron energy spectrum. We forward model through the atmosphere the predicted X-ray energy spectrum and flux. And then we develop this inversion method to then estimate the electron energy distribution. So what you're looking at, if just pay attention to the top row of plots here, in the center panel is a black line, which is the true energy distribution of electrons. Then you go over to the left panel, and in black, again, we simulate the photon energy spectrum. Then we provide this inversion method, which estimates the electron distribution and best fits the photon distribution in an iterative method. And that's the two red curves. So there's a red best fit photon distribution, which fits very, very well. And there's a red best fit electron distribution, which doesn't fit as well, but it kind of gets the general sense. And the error bars there are statistical estimates. Most importantly, on the far right panel is then the forward modeled atmospheric response. This is the ionization produced in the atmosphere between 30 and 150 kilometer altitude, as you can see. And our true and our estimated energy distributions give very, very similar profiles in the atmosphere. So this means that we're estimating it probably as good as we need to derive the response to the atmosphere. All right. So the three rows, by the way, are just different input energy distributions that we tried out. I will skip this. This is, we updated the method. The previous slide was the method not including knowledge of the energy distribution of the electrons. In the updated method, having added the electron detector to the mission, we use that as a constraint, and now we do even better in terms of estimating that energy distribution and atmospheric ionization profile. So I don't want to spend too much time on this because it's easy to get lost in all of these details. So I'll just go over quickly the mission design for APEX. This is going to be a low Earth orbit mission, so it's flying at about 500-kilometer altitude, and that's our goal, and looking down at the upper atmosphere. If we're at a higher altitude, then the number of photons that we will measure will be reduced by 1/r². And if we're at a lower altitude, then our field of view gets smaller. So we sort of tried to find the sweet spot there between a good field of view, which is about 1,000 kilometers, and a good flux of photons. We are a 6U CubeSat bus. We will be in a circular orbit at a reasonably high inclination. So the map at the top shows a polar orbit. That allows us to measure at high latitudes to be able to see the radiation belts as we fly over those high latitude regions. The polar region is not particularly important, but it ensures we cover all of the radiation belt regions. We are going to use the last ground station for data downlink and for communications. So the very bottom of the bottom picture, you can see the last building with the S-band and UHF ground stations on the roof. We use S-band for data downlink and UHF for command and telemetry. And then we don't care really about what's going on in the low latitude regions. Where we're below the radiation belts. So between plus and minus 40-degree latitude and during daytime, we will be sun pointing and or pointing at the ground station for downlink. And then when we are at higher latitudes for science, the mission will point down the magnetic field lines so that the particle detectors can see the electrons coming down the magnetic field lines. And there's some other interesting parameters here about the mass and power of this CubeSat. One of the hardest things about this mission is the power. The current design uses 26.5 watts of power, which is quite a bit for a 6U CubeSat and creates a bit of a heat problem. We are burning all of this power largely because of the X-ray detectors, and we need to carefully design the instrument in the spacecraft to be able to radiate that heat so that things don't get overheated. Here's a little bit more about that CONOPS. You can see the latitudes that we're interested in. So the L shells, which correspond to the radiation belts, are mapped to the surface of the Earth as shown on this map with the blue lines. And the region that we really care about are between about L equals 3 and L equals 8, so bounded by all of these blue lines. So we don't need to go below 40-degree latitude. We do sometimes need to go to almost the polar region, though, as you can see in that area over Antarctica. We've also determined how often we expect to see precipitation events from the radiation belts. And so the plot on the bottom is data from the POSE spacecraft. And we've used those to count over the last 20 years how many major precipitation events occur. And we expect to see something like 20 to 90 events per year, depending on the solar cycle and also just annual variation. You also notice that these are very well correlated with the DST index. That's just incidental. Well, it's not incidental, but it's interesting. The payload and the spacecraft look a little bit like this. The particle detector instrument is called AFIRE, and that's the APEX Fire instrument, and I forgot what FIRE stands for, but it's part of the Firebird mission. So it's a copy of the Firebird particle detector. And so that'll measure the electron spectrum. And then the X-ray instrument that we're developing is called AXIS, the Atmospheric X-ray Imaging Spectrometer. And this will measure the X-ray flux, the spectrum, and the spatial extent. And this is a little bit of an old picture, so I'll show you some new stuff in a second. So here's, again, just the AFIRE instrument. It's a copy of the instrument that was on Firebird. Measures electrons from 200 keV to 1 MeV with reasonable energy resolution. I think it's actually 12 bins and not 16. My apologies. And about 1 Hertz resolution. So this is actually a very simple instrument. It's half a U in volume. That's 10 centimeters by 10 centimeters by 5 centimeters. And only uses about 250 milliwatts of power. So it's small, it's light, it's low power. It's a great little instrument to add to a mission. Now the Axis instrument is quite a bit more complicated. This thing that we've created from scratch is an array of pixelated cadmium zinc telluride detectors. So each detector has 16 by 16 pixels. They're sensitive to photons between 50 and 300 keV. And the little detectors are shown on the far right there. And the design is based on a balloon instrument that was developed by Chris Cully at the University of Calgary. So he's a co-investigator on this mission, and he's helped lend his expertise to this design. What they did not use that we're using is this coated aperture concept. So in the instrument CAD model that you can see there are a bunch of square holes. If you're not familiar, a coated aperture is a grid of small apertures designed in a mathematically defined pattern that casts a shadow on the detector. And you can deconvolve the image that you get with the Fourier transform response of the coated aperture to get an image on the sky. And this is a reasonably common method of imaging high-energy X-rays, where you obviously cannot use lenses or other imaging techniques. So it's been done on a few larger missions, but as far as I know, it's never been done on a CubeSat. We also have to develop the housing for this instrument, which is using a method called a graded Z shielding, where we have layers of materials with different atomic number to absorb electrons and photons and so forth. So the layers that we have are tin, tungsten, and polyethylene, starting from the inside and going outwards. And we've done quite a bit of simulation of this design to see its performance. So here's a little bit more on that coated aperture imaging. Our design, I believe, has actually changed since this one, so I apologize for not updating it. We were initially using this Mura coated aperture that you can see on the top right with the black and white regions there. Very good. The different coated apertures have different performance for a point source versus a distributed source. We are trying to image a distributed source where the photons are coming from the entire field of view, rather than trying to image, an X-ray emitting star, for example. So there's various methods to do the inversion. It's not quite as simple as just an inverse Fourier transform, and don't want to talk too much about the details of that. So let me get into the spacecraft design quickly. Keep an eye on my time. The spacecraft is largely being developed at LASP, as I mentioned earlier. Here on the right is the entire block diagram. Those of you, I presume, you're all very familiar with spacecraft systems. So at the center, we have our command and data handling system, our flight computer. And then surrounding it, you see the guidance, navigation, and control, the GNNC. I usually refer to that as the ADCS, or Attitude Determination and Control System. We have our communication systems, our electrical power system, EPS, structure and mechanisms, thermal systems, and then, of course, the payload. Most of our flight electronics, that is the CDH, software, electrical power system, are all being developed at LASP. And so this is what LASP is calling their common bus, with the idea that they develop a EPS, CDH, and software system that can be reused on every mission to come, probably with minor changes every time. That's what usually tends to happen, but reasonably reusable. It won't exactly be an off-the-shelf system, but it will save LASP a lot of cost and time trying to find the right off-the-shelf component, for example. We are very happy with the ADCS system from Blue Canyon Technologies. That's the exact. And so we're using that little box. It's a half-U box, just under 1 kilogram, that provides very good attitude control and attitude determination, including a star tracker. We have our S-band and UHF transmitters and antennas. We are designing the structure completely from scratch. We're also designing the solar panels from scratch. and of course the thermal systems. So I'm just about to wrap up here on Apex, just to give you a status of where we are. The instrument itself, we've developed a prototype and built it and tested it. The electronics and detectors and everything are working really well. The software for the instrument works great. We just last week took it to Goddard Space Flight Center, NASA Goddard, and did radiation testing of this instrument. We put it in there. They have a thermal vacuum chamber with a beam that they fire a beam of high energy electrons at a target, in this case the instrument. And from that we can see how well the shielding works. We fire electrons at the shielding wall of the instrument and then see how many counts show up on the detectors on the inside. And the data, that was just last week, so the data from that is still under analysis. We're now moving on to developing the flight instrument, and you can see the updated CAD model for that instrument in this bottom center with our new coated apertures and new housing and thermal straps on the side to pull heat out from the instrument. The particle detector instrument is almost finished, being built over at UNH. We've also developed a FlatSat, that's the box at the top center with the flight avionics boards in there. And one really fun thing we did is 3D printed the entire structure and all the pieces that go in it to help us figure out where we have problems in the design. And this is really nice because it's a low cost, relatively quick way to build the entire system, start putting things together like Lego, and figure out what's not going to work. You know, for example, the dark blue box, which is the Axis instrument, is very, very close to the AFIRE instrument. So we have to make sure that cables are routed from the right side so that we can't have connectors coming out the sides that are touching, for example. So that's been great, and we're moving on to actually building the flight structure very soon. Like I said, this mission should be ready by summer of next year and then hopefully launching shortly thereafter. We're awaiting news from NASA's CubeSat Launch Initiative, CSLI, to tell us when and on what rocket we would be launching. Okay, so I'm going to come to this slide a couple times with the next two missions as well. And what I'm doing here is comparing and contrasting our approaches to these different missions. So for Apex, like I mentioned, we have a common bus that's being developed by LASP and is really LASP's intellectual property. Plan to reuse that on future missions. We have, for Apex, a very unique low TRL instrument that has great potential. I've actually had interest from a few other groups in putting this instrument on their missions in the near future as well. Apex is largely being developed by LASP engineers, but with lots of support from graduate students. Operations is at LASP, as I mentioned. When we actually get to operating the mission, we will have professional mission operators that are hired at LASP that have done this for many large missions as well. But we also hire student operators who are mentored and trained by those professionals. Apex has obviously quite a bit of student training, and we're providing experience to students, but it's not the key focus of the mission. And as I mentioned, I think the main innovation for Apex is the instrument and the science that we're going to do with it. And so I'll come back to this slide with the other missions to show you what I think are there, how the approaches differ. So let me talk about Canvas now. And these will be hopefully quicker because I'm not going to have too much time. The Canvas CubeSat mission is aimed at understanding the injection of energy, VLF radio wave energy, from the ground into the magnetosphere. And so that radio wave energy is largely input by lightning and by ground-based VLF transmitters. So these are in the hundreds of hertz to 50 kilohertz, the frequency range of interest. And the picture on the top right shows you kind of what happens. In step one, lightning emits an electromagnetic pulse. The VLF energy from that radiates in the Earth ionosphere waveguide below 100 kilometers, but some of it also leaks through the ionosphere. Then it propagates into the magnetosphere in the picture on the right, number 2, as a Whistler mode wave. Those waves can essentially leave their energy in the magnetosphere, but they can also resonate with radiation belt electrons. And then just like with apex, those energetic electrons can precipitate into the atmosphere on step 4 and disturb the upper atmosphere and ionosphere. So apex, while apex is not specifically focused on lightning-induced precipitation, the concept here is the same, that we have energetic electron precipitation being kicked into the Earth's upper atmosphere by different mechanisms, but in this case, those mechanisms are lightning and transmitters. So we want to understand how much energy from lightning actually escapes the ionosphere, that helps us to understand the impact, the total quantitative impact of lightning on the radiation belts. The picture on the bottom right, by the way, are examples of what are called these Whistler mode waves measured in a spectrogram. So these are showing 0 to 20 kilohertz and 1 second of time. And this is data from the Demeter mission, the French mission from 2004 to 2010. And there hasn't really been a low Earth orbit mission to study these waves since then. So CANVAS is actually really a follow-on from the Demeter mission. And I have to take that back. I always say that, and then I correct myself. There's the ZH1 mission from China, which makes a similar measurement. Now, the management approach for CANVAS is quite a bit different. We are largely leading this development in the aerospace engineering department with some support from LASP. They're helping us with software, they're helping us with science, and a few other details. So this mission is almost entirely student developed, and it's actually incorporated into a graduate class that we teach with about 10 students taking that class each semester. So these 10 students each take on a role: project manager, systems engineer, instrument lead, comms lead, you name it, where they work on the development of the mission. We also have undergraduates working on it through an apprenticeship program, and we also sometimes have volunteers. When we get to mission operations, we will actually fall back to LASP and students as well. Now, under innovations, CANVAS is unique in that it has a 5-channel VLF receiver built into a 4U CubeSat. So that has definitely not been done before. We couldn't quite fit it into a 3U CubeSat, so we had to make it a little bit bigger. You'll see in a second, we have search coils which measure the magnetic component deployed on a 1-meter-long carbon fiber boom, which is also quite unique. We're including 3D printed components to hold those search coils, 3D printed in PEEK, which is a hard, thermally invariant, non-conductive plastic. We have bus electronics, including the CDH and EPS, that we've completely designed from scratch in our department. And when I talk about Cosmo next, you'll see that we're sharing that bus. So we're creating our own sort of common bus at the same time. This CANVAS is a mission funded by the National Science Foundation, which we're very grateful for, but it means that the budget is a lot lower compared to NASA. It's about 1/4 of the total budget. And we're trying to do a fairly complicated mission with a lot of science. That means that education is a key component because we can't afford to pay professional engineers. And our expected launch is similar. We expect to be finished with the development of this mission by next summer and going into environmental testing and be ready for launch towards the end of 2022. So really quick overview on the science of this mission again. It stands for the climatology of anthropogenic and natural VLF wave activity in space. I've already told you a little bit about the science, so I won't repeat the questions here. You can see the mission, the spacecraft on the top right. It's, like I said, a 4U long CubeSat with deployable antennas, deployed solar panels, and then this long boom that sticks out the back of the spacecraft and has the search coils at the far end. The two science pictures here, the data, show you some of what we're trying to understand. The bottom left shows the difference between models from the 60s and models from 2013 on the absorption of these VLF waves through the ionosphere. And you see a huge difference between these models. And it speaks to the fact that we need very well calibrated data to really explain which of these is correct or if either of them are correct. And the picture on the right assumes the newer model, the 2013 model of ionospheric transmission, and then calculates the energy density over the course of a year. So this is average energy density for daytime and nighttime on the top and middle plot as a function of L shell and longitude. And so you can see where we predict the energy to go. And we can measure this. L shell and longitude is just like on Apex, is very similar to latitude and longitude. And so the goal is that with the mission, we'll develop a map like this, but based on data and not based on modeling. The payload for Canvas, you can see here. I've mentioned the search coils. The search coils at the top center there are the little 9-centimeter long cylinders. And they were actually donated to us by LPC2E in France. That's the same laboratory that built the search coils for the Demeter mission, as well as Parker Solar Probe and Solar Orbiter. They're very much search coil specialists. And you see the search coils mounted in our 3D printed structure. So that's our peak 3D printed holder that holds the 3 search coils orthogonal to each other and in the optimal orientation to fit into the back of our CubeSat. The preamplifier board is the circular board that you can see that fits within that holder. And then that is the signal from the preamplifier is fed to our analog receiver, which is the board on the top right. And there's 5 channels there of the receiver electronics. So 3 of those channels are for the 3-axis magnetic search coils. And then the other 2 channels are for electric field. And on the far left, you see the CAD model of our electric field antenna system. So there's a crown, what we call the crown, the 10 by 10 centimeter lid on the end of the CubeSat. And the hinges are integrated into that, and antennas come out of those hinges. And the preamplifier, the electric preamplifier board is integrated into that crown. So all of these components have been designed and developed in the aerospace department at CU. Excuse me. We also have, after the analog board, there's a digital board that does all the processing of the signals. And I'll say a little bit about that in just a second. There's some arrows. The spacecraft looks like this if we look at the internal guts of it. So you can see the search coil and preamplifier at the far left of the CubeSat in the back. They take up a decent amount of space, basically 1 U. And then behind that is the deployable boom structure. So the deployable boom in white is this box, which has a rolled up carbon fiber tube that's been flattened and rolled up on a spindle. And then as it unspools, I don't have a video, I apologize. As it unspools from the deployer, it snaps into a tight cylinder in the other direction and forms a rod, essentially. And so that will hold the search coils in place and also carry signals and power along that boom. The other components you can see, there's a stack of 5 electronics boards, which include the S-band radio, the analog and digital boards for the instrument, and then our CDH and EPS boards for the flight computer and power systems, of course. And we managed to squeeze in the same exact ADCS system from Blue Canyon, UHF radio, S-band radio and antenna, batteries, deployable solar panels. So it was quite a challenge to stuff all of this stuff into the 4U structure. But it looks like it's going to work. Some of the components I think that are unique, I talked about both of these already. The search coils and the 3D printed peak holder are pretty unique. And then this carbon fiber boom. So you can kind of see how it works here with the boom just sticking out of the structure on the right. And then when it's deployed, it makes a nice rigid tube that's 1 meter in length. And the way that it works is it's a memory-shaped carbon. And that's been developed by a company in Colorado called CTD, Composite Technology Development. And so we've outsourced that part to them. Canvas mission is pretty simple. We're also aiming for 400 to 500 kilometer altitude, a circular orbit, at a lower inclination. We don't need high latitudes since we mainly want to fly over lightning regions. So 51-degree inclination, which would allow us to be deployed from the International Space Station, is what we're aiming for. We do want to have a 1-year mission, so that means we actually need an altitude slightly higher than the International Space Station, because our drag calculations say that from the ISS will only last about 6 months. So unfortunately, there are launches which take you to the ISS, and then they leave on what's called the Cygnus vehicle. They leave from the ISS and go up to a higher altitude, to all the way up to 500 kilometers, and then they deploy CubeSats from there. So that's what we're aiming for. We have a decent amount of this one has less power. It only requires 16 watts of power to operate. One of the big challenges is that we're producing a ton of data, 240 megabytes a day, and our ground station is not quite yet capable of downlinking all of that data. So we are working on that problem, and it's a complicated problem. It's not as simple as just finding another ground station. But we're on a path to solving that problem soon. Now, I'll say a quick bit about the science here. We extract the wave parameters as follows. We measure between 0.3 and 40 kilohertz on the 2 E field and 3 B field channels. And then there's a method that was published almost 20 years ago by Andrei Santelik, which allows us to extract wave parameters from those 5 components. So in half a second or 1 second intervals, as shown in the top on the panel on the right, we can estimate the pointing flux as a function of frequency, as well as the k vector direction, the wave vector direction, in 2 angles, theta and phi, the planarity of the wave, the ellipticity of the wave, other things like that. So we're actually doing that calculation on the ground, but we're doing part of the processing on the spacecraft. And that processing happens in an FPGA on what we call our digital instrument board, and it allows the data to be heavily compressed before downlinking. Even with compression, though, we're still having that huge amount of data to downlink. So here's our status and schedule. The structure is nearly complete. On the far right, you see the actual machined crown piece that will hold the electric field preamp and antennas, and 3D printed versions of the panels. So we 3D printed the panels in order to assemble it again and see how things fit and see if we've made any major mistakes. And then once that's finalized, we should only have to machine the panels once out of aluminum. The avionics boards are all nearly completed. So these are the boards that we've developed in-house from scratch, the CDH EPS and so forth. And on the CAD rendering on the top, you can see what we call our flat sat, where we've got each of the 5 main boards attached by connectors to our GSE board, our ground support equipment. And that ground support equipment board will be replaced by a backplane in the final version for flight. Just essentially shrunk down and put vertical connectors to stack things. We've built our antennas, taken them outside, and our antennas and all of our instrument electronics, taken them outside and done measurements. And this spectrogram that you can see in blue on the bottom center, that is actual data from our little CubeSat antennas measured outside. And when I first saw this, I was so excited because this is better than I could have expected in terms of the quality of the data and the signal-to-noise ratio. All the vertical lines you see are lightning that must be somewhere in the middle of the United States. And the horizontal lines around 24, 25 kilohertz are well-known VLF transmitters, one of which is in Seattle and the other is in South Dakota. Hawaii, we can see the transmitter from Hawaii, and we can actually just faintly see a transmitter from Puerto Rico as well, just above 40 kilohertz. So this is very exciting. All this is to say that things are coming along well, and we're expecting, again, to be ready in the middle of next year. So here's our comparison slide again. And so compared to Apex, you notice some differences. We've developed the bus ourselves. It's a relatively unique bus, as I say. And it's unique in that it's largely been designed and developed by students. It's the same as APEX. We have a unique low TRL instrument with great potential for new science. Compared to APEX, this mission Canvas is student-led with some LASP engineering support. And looking down at education, you see how that's affected. As I mentioned, Canvas is integrated into our graduate projects class and involving undergraduates through research experiences, with then just some help from LASP. So it's very, very student-oriented. The innovations, again, are the instrument, the deployable boom, and 3D printed components. Okay, so finally, in sort of the next, I'll make this very quick, I'll talk about the Cosmo mission. Cosmo is a little bit different. It's not exactly a CubeSat for space science. The goals of Cosmo are to measure Earth's magnetic field, and that's it. But it's to measure the Earth's magnetic field very precisely with both the scalar magnitude of the field and the vector 3 components of the field with better than 5 nanotesla precision. And this is required to incorporate into magnetic field models. Those models include the IGRF, the International Geophysical Reference Model, and the WMM, the World Magnetic Field Model. And the WMM is the one that's used by governments and militaries around the world for precise navigation. So the goal, what you're seeing here on the right is the SWARM mission on the top right. And SWARM is currently the mission, which consists of 3 satellites. It's a European Space Agency mission that provides data for the World Magnetic Field Model. But SWARM will not last forever. And so the US government was looking for solutions for what will come next. And we told them we can do this on a CubeSat. And so that's what we're working on. Now, Cosmo is led by the Aerospace Engineering Department, again, similar to Canvas. It's again, it has been incorporated into our graduate projects class, but it's also largely collaborating with LASP and also with the Mechanical Engineering Department and a small company that's building our magnetometers. The innovations for Cosmo, it includes a vectorized optical magnetometer, which with roughly 2 nanotesla precision and accuracy. And this is a device that has never flown in space before. I take that back. There have been vectorized optical magnetometers on SWARM, but ours is unique in that it uses rubidium. We also are developing our 6U CubeSat structure specifically for magnetic cleanliness, and I'll say a little bit about that in a second. And the bus is similar to Canvas. I'm going to skip some of the other details. So I mentioned this already. The main goal of this, the motivation, is to provide measurements of the Earth's magnetic field. The picture on the right is the actual World Magnetic Field model from 2020. It's a model that's updated every 5 years. This is the declination. So 3 components of the field on the surface are the intensity, the declination, and the inclination. You can also do the XYZ components if you want. Like I said, data is currently from SWARM, but that won't last forever. So Cosmo is our plan to replace this. The concept is that we build a 6U CubeSat in a sun-synchronous orbit, day-night. We take data on the night side. During the daytime, there's simply too much noise from the solar panels. And we can do this with one spacecraft, one 6U spacecraft. If we develop it for a 3-year mission lifetime, then we can launch a new one every 2 to 3 years and ensure a continuous record. And this provides reliability, a contingency plan in case of failure. We can always build a new one and put it up very quickly. And it's a very cost-effective solution. The budget for this over 20 or 30 years is much less than one big mission. The instrument is a key part of this, again. So we have a scalar magnetometer based on rubidium that we vectorize by wrapping coils around it and exciting those coils in 3 different directions. This provides all 3 vector components at 1 Hertz time resolution, as well as the scalar measurement at 100 Hertz. We have to have electronics for the scalar magnetometer. We also have to have electronics that drive the vector modulation. And we also have digital electronics to collect the data and process data from these 2 star trackers. The star trackers have to be installed near the magnetometer on an optical bench to ensure very precise pointing knowledge. We have to know where the magnetometer is oriented in space, in 3D space, to within about 7 arcsecond accuracy to provide the required accuracy of the field components. So we design an optical bench which ensures thermal stability and use 2 star trackers to give us that 7 arcsecond accuracy in all 3 directions. And there's some numbers on mass and so forth. I'll kind of skip over this again because of time, but the scalar magnetometer operation is shown here. I apologize, I'm running out of time, so I can't go into too much detail. Our spacecraft, I think, is a really unique feature of this system. We went with what we call the long 6U orientation, which has only been flown once or twice before. And the reason is to isolate the magnetometer at the far left of the instrument from the noisiest electronics, which are the exact. The exact ADCS system has torque rods and reaction wheels within them, which have magnetic materials and currents, and they will produce magnetic noise and biases. So we're far enough away, and we've actually tested this to ensure that the noise is below our requirement. But we also have a ConOps scenario where we can turn the torque rods off when we want the most precise data. And the reaction wheels are not quite as noisy. Now you see all the other components in here that are very similar to Canvas. We have our S-band antenna, our S-band radio, our EPS and CDH, batteries, et cetera, et cetera. We have taken each of these components. So in this table, on the top green row, you can see all the different parts of the CubeSat. And we have measured the noise and bias. So you see noise RMS and then bias at the very bottom from each of these components. And we add all of these up together in quadrature to see what are the noisiest parts of this spacecraft. And what's the total noise and bias that will be seen at the magnetometer. So what you can see is that at 1 hertz, where we need the vector measurements, we're sitting at about 3 nanotesla of noise and something like 40 nanotesla bias during nighttime when we don't have the solar panels making a bunch of extra noise. And that's also with the torque rods off. So that gets us under our 5 nanotesla requirement. And the bias can be largely calibrated and removed. So we have to do a lot of careful characterization when we get close to completing this mission. So status and schedule again. The spacecraft bus is nearly complete and ready to manufacture. The avionics are as ready as they are for Canvas. However, our sponsor, which is the US government, has asked us to pause the spacecraft development and focus on the magnetometer instrument for the next year or so. So the spacecraft is going to sit and we're going to manufacture it a year from now. And in the meantime, we're going to focus on building up the magnetometer and testing and characterizing its performance. So the picture on the center is our prototype vectorized system with the scalar magnetometer is at the center of it. And so we're working on testing this thing and modifying this design. So that's what we are working on right now. So again, comparing the approaches, Cosmo is more similar to Canvas. You'll notice the bus is the same. It's integrated into graduate projects for education. Has a unique instrument. The structure is another unique component of Cosmo. It kind of falls in between in terms of the personnel. So there's more professional LASP involvement, but there's also the graduate project students. So we have both student involvement and professional involvement. So with that, I'll spend just the last couple minutes here talking about some of these different approaches. If you're developing a new CubeSat mission, what's the best way to go about this? It obviously depends on your institution. If you're a university, then you're going to be incorporating student effort and education and training as part of this process. But often we want CubeSats to be operational missions or science missions, like APEX, with a focus on the science results. And so education is great. but we really need to get it done and make sure that it works. So that's one of your choices, and I'll talk about this in a second, between professional engineering versus students. The other one is with the bus and the avionics components. These days, you can buy CubeSat components off the shelf, the EPS and CDH and radios, even structures, or you can build them in-house. And it's not always an obvious decision which one you should use. So I'll talk about the bus selection here quickly. Like I said, you can buy a spacecraft structure from a variety of different companies, like I'm shown at the top right here, just the structure itself, and then figure out how to mount all of your components. It's a little bit limiting that way because the apertures are going to be what they give you. You can also go with a complete commercial bus. So Blue Canyon started developing the entire spacecraft bus. That includes the structure, the EPS, CDH, ADCS system, radios, solar panels, everything except the instrument. And a couple of the missions at LASP have taken this route, where they buy the bus from Blue Canyon and then build the instrument and integrate the instrument into the bus. One of the disadvantages of this is that it's expensive and you lose a little bit of control over how the systems work. You also don't have the intellectual property, of course. So Apex has taken the different route where we decided to build our own spacecraft bus. We're buying the ADCS system and the radios from off-the-shelf companies, but we're building our own EPS, CDH, interface board, potentially building our own batteries, structure, solar panels. This gives us control over the spacecraft design, allows us to put apertures where we want them, fit the solar cells around all the instruments, for example, decide where we want the antennas to point. And it builds that in-house expertise that we can use for future missions as well. Now, the biggest downside is that it takes time and personnel with expertise and ends up not necessarily being much cheaper than the off-the-shelf bus. But that in-house expertise and control, I think, is very valuable. Now, that sort of ties into the personnel decision. Do you build your mission led by students or by professional engineers? As I said, as a university, education is a critical part of why we're doing this. So the pictures on the right show you some of the student teams that have worked on some of those previous CubeSat missions. Minx, CSSWE, and Maxwell on the bottom left. With students, the cost is lower, enthusiasm is high, they bring new ideas, but they don't necessarily have the experience, so it takes longer, requires mentoring and training. But like I said, that's really why we're here. If you go the approach of using professional engineers, of course, then it can be much quicker due to that experience and probably more reliable, but definitely more expensive. And then often we go with an approach that's somewhere in between. We use students to do a lot of the work, but they're mentored by professional engineers. And that's a great model because the professional mentors sort of provide the oversight and just make sure that things aren't being done completely stupidly. And they have some experience, quite a bit of experience on things that have gone wrong in the past and can help guide the students to avoid some of those pitfalls. One of the challenges, of course, though, is that these professionals have other things to do, big missions that they're working on, and so they don't always have a lot of time available to help out on the side with these things. But we've been very lucky at LASP that the folks there are very happy to help with these CubeSat missions. So again, here's my comparing approaches slide, and I just really want to highlight here, looking at Apex, Canvas, and Cosmo. One of the things that I really like about CubeSats, and is common to the 3 CubeSats that I'm working on, is the instruments and the science. These CubeSats really give us the opportunity to try to develop new, unique instruments that haven't flown before and do really interesting science with those instruments. So I think of myself more as an instrument person than a satellite person. And that's where I think there's just some of the great value in CubeSats. And that's it. I'm at my last slide here. I don't need to read this for you. It's just a statement about each of the missions. I have to acknowledge the sponsors, the NSF and NASA for Canvas and Apex. And I didn't have a logo, but it's the National Geospatial Intelligence Agency, which is sponsoring Cosmo. And so we're very grateful for their support. And I'm very grateful for all of you and your time and listening to me give this presentation. So thank you all very much.
Thank you very much, Bob. That was a very comprehensive presentation. And actually, I think you actually managed to answer most of the questions typed into the chat. I would like to ask one more question, though, regarding the concept of a common bus developed and maintained at an academic institution. So this is an issue that we've also been looking at. And certainly, the idea, as you mentioned, the idea of having control and the know-how to customize a common design for different missions is certainly very attractive. But one problem that we've run into is we have a very good student team who developed our first spacecraft. We're going to continue to improve that. But as you know, the lifetime of a student workforce is very limited. How do you continually keep that know-how within the group, and how do you continue to maintain and revise this common design?
Yeah, that is really the hardest question for sure. Again, at LASP, of course, you have the professionals that have been around for a while, folks like Tom Woods, that know everything about the Minx mission and all of the development of their bus electronics through that cycle. And folks like Rick Conert at LASP who know the new common bus system that they're developing now and will be able to keep that institutional knowledge. As you mentioned, in our department with students, we have the turnover problem. So we've sort of, I said it was from scratch. It's really actually inherited from the Maxwell design, which was inherited from the QB50 design, and that was inherited from the Minx design. So the Aero Common Bus has actually evolved from Minx as well. We've made some changes to it, and in my group, I have an electrical engineer who is full-time, and he's the one that's really managing that system and making sure that we develop a bus that works for Canvas and works for Cosmo, and we're sort of thinking about making sure that it'll work for some future missions as well. And we've been having LASP help us sort of consulting to say, yeah, that's a good idea. That'll probably be useful for future missions. So yeah, the short answer to your question is I don't know how well it's going to work into the next phase of missions from our department. But it's always the hope that we'll be able to reuse what we've built, right?
Hopefully. I'd like to mention that our own 3U spacecraft has a Minx heritage as well. So, so I think there's going to be a lot of new spacecraft designs coming from that. So we have a question from Tiger Liu. Okay. Tiger, do you want to turn on your mic?
Oh, sure. And Bob, I just wonder, what's the reason your Canvas is, with this incarnation about 50? Because if you a little bit higher, you will be able to observe the so-called plasma pulse. Because ULF wave, that one is very important. It's actually, if you focus on the measuring the, the via wave propagating from the Earth to the magnetosphere, but the magnetic pulse actually is one of the most prominent, the area to be studied.
Are you suggesting for VLF or for ULF waves?
Oh, okay. I got you now. So if you go by, the ULF, because you mentioned the Demeter, because I work on Demeter and also Zhangheng, and those satellites allow us to, in fact, study the plasma pulse. So
sorry, I'll admit that Demeter had a much better response at the lowest frequencies compared to us. They were more sensitive all the way down to ULF, could really get signals even into the tens of hertz. But our mission is going to really be limited to about 300 hertz and above. So we're not going to have great ULF measurements.
Oh, okay. Thank you. So actually, that's the reason why I'm curious, because like I say, it's those are some pronounced, the activity over the Whistler that will be around the plasma pulse area.
Yeah.
And one more question is regarding the cosmos, because since if you use the scalar magnetometer, which means is you only have a total, right? You don't have three components.
So we use a scalar and we vectorize it. We excite. I didn't get into the details, but we essentially put 3-axis Helmholtz coil around the scalar.
Oh, okay, gotcha.
And we modulate it. We modulate it at predefined frequencies, and you can, with some math, you can extract the vector components from the spectrum of the scalar measurement.
Oh, that's a very smart approach, because you can get by those boom. Okay, thank you. Yeah, okay, thank you.
Okay, we have time for one more question from Christian. Christian,
sure.
You on your mic?
Thanks for your talk. On page 10, you mentioned that you had 26 or 27 watts of power budget, and that's kind of the wiggle area between, smaller CubeSat has, or like 3 unit or something has a total power budget of 26 watts, or with a nicely built larger CubeSat, you can also get a bit more. So I was wondering, what's that 26 watts? Is that your total power budget for your entire satellite? Or is that you really want power for your instrument, so that's just your instrument?
Yeah, are you thinking of the Apex mission here?
Yes, sorry.
Yes. So when I showed the 26 watts, that's sort of the orbit average power.
Okay.
The consumption of the whole spacecraft. So when the instrument is on, it's even higher than that. It's 38 watts. And then 26 is orbit averaged. So we need solar panels that can generate 26 watts orbit averaged, which is ends up being about 80 watts peak from our solar panels. So we've designed the panels. You saw the big deployed panels for Apex to generate that much power. But as I mentioned, especially with CubeSats, when you get to that much power, even on a 6U, I think the biggest challenge is getting the heat out.
Yeah, probably, and I guess you also need to do quite a lot of protection for your battery, because otherwise you're going to wear that thing down like crazy.
Yeah, so the battery is just simply over-designed. We design so that it's only discharged about 30% at the most. So we have like a 75 watt-hour battery that only ever uses 20 watt-hours. Does that make sense?
Yeah, cool, it does, thanks. Can you, by any chance, share any cost comparison or cost estimates between Apex and Canvas? I'm curious for direct cost comparison between student-built and institutional. Yeah,
I'm happy to. So, and this is all, it's government funded, so the dollar amounts are actually available online. With NSF, their standard CubeSat budget is 1.2 million US. So that's our budget. And about 300K of that goes into the hardware and the rest into labor. So we are using some of it for labor for management, of course, and operations and so forth. And then Apex is $4.7 million from NASA, which includes actually some of the launch costs. So it's a little bit over $4 million to develop the entire mission. So that allows us, obviously, quite a bit more labor, off-the-shelf components, and so forth.
Okay, thanks a lot, Bob. Really appreciate your presentation, and it's definitely definitely helps to increase our understanding of both the missions and also the different development models that are available.
Yeah, great. Thank you all very much for your time, and my apologies to Tom for running into his time.